All right, we're now on section 5.3, enthalpy. So in this section, we're going to state the first law of thermodynamics, define enthalpy and explain its classification as a state function, write and balance thermochemical equations, calculate enthalpy changes for various chemical reactions, and explain Hess's law and use it to compute reaction enthalpies. So this section is fairly long and very dense. So don't be afraid to stop, rewind, replay certain parts. Ask me any questions you may have. Make sure to do practice problems. You can use the problems in your book, the homework, etc. And make sure you really do understand this stuff. So let's first talk a little bit about thermochemistry. And this is a branch of thermodynamics, which deals with the relationships between heat, work, and other forms of energy. And substances are reservoirs of energy, so we can add energy to them or take it from them. And we can store it in a substance when the kinetic energy of the atoms or molecules are raised. So the total of all possible kinds of energy present in a substance is called its internal energy. And it's generally symbolized with a U, sometimes an E, but U is actually the most common. And the first law of thermodynamics focuses on the relationship between the change in internal energy, delta U, heat, the same heat we've already been talking about, Q, and work. Okay, so the first law of thermodynamics tells us that the change in internal energy of a system is equal to the heat plus work. And this is one version of the first law of thermodynamics. We're going to talk about a few different versions of it. So energy can be transported into a system, which increases the internal energy, giving us a positive Q. So if the system absorbs heat, we have a positive Q. But if it's the surroundings doing work on the system, so maybe something pushing your system, then you have a positive W. We can also take energy out of a system, resulting in a decrease in the energy, either if our system is releasing energy, giving us a negative Q, or the system itself is doing work on the surroundings. So it's pushing out, for instance, into the surroundings. That gives us a negative W. Okay, so here's a little picture, okay, where the green is our system, and the system has its own change in internal energy, delta U. Okay, it can either be less than 0 or greater than 0, depending on what's happening. If you have heat leaving and work being done by the system, that's what it means by W by, we're going to have a negative delta U. Or if you have heat entering the system or work being done on the system, then we have a positive delta U. So one type of work is called expansion work or pressure volume work. So this is when the system is pushing back the surroundings against a restraining pressure. So the surroundings are compressing your system. Okay, so this is like an internal combustion engine. So when the combustion is happening, the products are pushing onto pistons in the engine. This is my beautiful drawing. Okay, and they're pushing up on the pistons in the cylinder. Okay, so the system is losing energy by heating up and doing work on the surroundings. So the internal energy is going to decrease. And because this is consistently happening, this work that's being done on the surroundings and the heat being produced, it keeps the engine going because we're continuously making this energy. So again, our system in this case for the internal combustion engine is our gasoline and oxygen, and the surroundings, the rest of the universe, including our engine. This is an exothermic reaction, so heat is giving off, and the reaction is pushing the pistons out, so we are doing work on the surroundings, giving us a negative W. So negative Q and a negative W, we are decreasing our internal energy of our system. Now, internal energy is an example of a state function or a state variable. And what this means is it doesn't matter how we get to the value, it's only dependent on the actual state the system is in. So for instance, the altitude of a mountain. Okay, if we are climbing Mount Kilimanjaro and we get to the top, yay, we're not one of the 10% of people that don't make it. Learned about that in one of my true crime podcasts I listened to. Okay, it doesn't matter if we go straight to the top or if we take a winding road. No matter what, at the top, we're still at 5,895 meters high. Okay, doesn't matter how we got there, it's still the same height. So that's what internal energy also is. It's a state function. I'm sorry, it's not Kilimanjaro, that's only 10%. That 10% of people die, that's Everest. Not sure what the numbers are in Kilimanjaro. Nonetheless. So, we have a property called enthalpy that we use to describe the thermodynamics of chemical and physical processes. And it is related to the system's internal energy and the product of the system's pressure and volume. So we use H to describe enthalpy, okay, not entropy, enthalpy. Okay, so it's equal to our internal energy plus pressure times volume. Enthalpy is also a state function. It's very important to know and to understand in what we're going to be doing soon. So we can't measure enthalpy directly, but we can measure changes in enthalpy, or delta H. So because of that, we also, since we're looking at a change in enthalpy, we're looking at the change in internal energy. And generally, we can assume constant pressure. Okay, so we could say constant delta T times delta P, but if pressure is the same, it's just P delta V. Okay, with the same pressure. So our change in enthalpy is equal to delta U plus P delta V. And this P delta V represents the pressure volume work. Okay, so pressure times the change in volume is equal to negative work. So this is another equation. I believe you actually need this equation in one of your homework problems. When we are at constant pressure, our heat we call QP for constant pressure. Okay, and like we said, remember negative work is equal to P delta V. And so then we can do some substitution. Where was I? So delta H is equal to delta U plus P delta V. Okay, and we know that P delta V is equal to negative work. And we also know that delta U is equal to Q plus W. Okay, so we can put that in. So delta H equals Q plus W. And P delta V is equal to negative work. So we can substitute that in for P delta V. And we're going to call this QP since this is constant pressure. And so we see that the works cancel out, and we find that delta H is equal to our heat of reaction at constant pressure. So lots of substituting variables in to get to this cute little equation, delta H equals QP. So what that tells us is the work done is caused by expansion or contraction. Okay, if the only work done, then the heat flow, like our QP and our enthalpy change, are the same. They're equal. So a lot of times we do experiments in open containers so that they are under atmospheric conditions with constant pressure, because the pressure around you in a room doesn't really change. So enthalpy is a very convenient choice for figuring out heat of a system. So we use thermochemical equations to represent the changes in matter and energy. And so the way these work is you have your reaction, your balanced equation, and then next to it you'd see delta H and a value. Okay, and so this gives us the amount of heat associated with the reaction as it is written. So in this case, we see a negative 286 kilojoules. That means heat is released. That means this is exothermic. And this also is telling us that 1 mole of hydrogen gas reacts with half a mole of oxygen to form 1 mole of water. And in doing so, negative 286 kilojoules of energy are released. If we were to multiply the equation by some factor, the delta H also needs to be multiplied by that factor. So again, when your delta H is less than 0, that means heat is released, you have an exothermic reaction. When it's greater than 0, you have an endothermic reaction. And one thing that you can also see is that when we go from hydrogen gas and oxygen combined to be water, we have an exothermic. But going the opposite direction, water becoming hydrogen and oxygen, it's the same delta H, but opposite sign. Okay, so if you reverse the reaction, your value of delta H, the sign of it gets reversed. If you multiply the coefficients of your chemical equation by a factor, you have to do the same thing to delta H. It's an extensive property, so it depends on things. So if I took this chemical equation, I multiplied everything by 2, delta H has to get multiplied by 2 as well. If I multiply everything by 1/2, it has to get multiplied by 1/2. Okay? You also have to make sure the state of the reactants and products are shown. So when you are looking at this, you need to make sure you write them, because different states of the compounds will change delta H. For example, if instead of making liquid water from the reaction of hydrogen and oxygen, we made gaseous water, we have a different value of delta H. So it's very important that you look at the states of matter and that you write them down when you are doing these problems, so you don't write the wrong thing down and you make sure things are matching up. Yes, that means there's going to be problems you have to do with this. All right, let's look at an example. Before we go to this one, I'm going to go to a blank screen and do a different one. We are told that 0.0500 moles of HCl reacts with 0.0500 moles of sodium hydroxide, and that forms 0.0500 moles of sodium chloride. These are aqueous. And 2.9 kilojoules of heat are produced. And we want to write the balanced thermochemical equation for the reaction. So one thing we know is when we react an acid with a base, a strong acid with a strong base, we make a salt and water. So they didn't specify water here, but we know that's a product. Okay. Now we know that for the reaction, we're told that we release 2.9 kilojoules of heat. So we can say that our delta H, okay, we can go ahead and use the HCl. It doesn't matter what we use. We're going to go ahead and use reactants, though. We're not going to use the products here. Delta H is equal to 0.0500 moles of HCl. Oops, sorry. That's not what I wanted to say. I wanted to start with our kilojoules. Negative 2.9 kilojoules of heat. And these kilojoules are produced for every 0.0500 moles of HCl. And we want kilojoules, and we can multiply this times 1 mole to say we just want this kilojoules. We don't need moles. And this calculates out to be negative 58 kilojoules. Okay, you could also leave it as kilojoules per mole. That's perfectly fine too. But our thermochemical equation then is HCl aqueous plus NaOH aqueous becomes NaCl aqueous plus liquid water. And delta H equals negative 50. Oh, and we put next to it, if I had enough room, delta H equals negative 58 kilojoules. Okay, so basically you're just taking your kilojoules for every mole and then saying, okay, and now assuming it's 1 mole, this is how much it would be. And again, you could do this for any of the moles. You'd get the same number if you did it for sodium hydroxide. You do have to take into account the stoichiometry. Okay, this is all 1-to-1, so that's where that 1 mole comes from. This is 1 mole of HCl, and now it's gone. Oh well. But that's where that comes from. So if you had a 2 for coefficient in front of whatever it is you're calculating, then you're going to also have to incorporate that into your equation. All right, let's look at this example. A gummy bear contains 2.67 grams of sucrose. When it reacts with potassium chlorate, all that heat's produced. This is actually a really fun thing to watch. I recommend looking this up on YouTube. Write a thermochemical equation for the reaction of 1 mole of sucrose. So that's where that other 1 mole came from in the last example, because we're told 1 mole of HCl. So now, we aren't given moles here. We're not given stoichiometric factors. We're given grams of reactants. We cannot do anything until we know our limiting reactant. So we have to figure out if it's sucrose or potassium chlorate. So if you remember, the first thing we need to do is turn everything into moles. So starting with sucrose, it has a molar mass of 342.3 grams per mole. Now, your book does this a little differently, and I'm going to talk about that also I'm going to do it how they do here, and we'll talk about that in a second. 0.00780 moles of sucrose. We're going to do the same thing for potassium chlorate, 7.19 grams, KClO3, 1 mole of KClO3. or 122.5 grams of it. And this gives us 0.0587 moles of potassium chlorate. So based off the stoichiometry, we know that there needs to be 8 moles of potassium chlorate for every 1 mole of sucrose based off our stoichiometry here. So we're going to go ahead now and do 0.0587 moles of the potassium chlorate divided by our moles of sucrose. And this is 7.52. So I do not have enough sucrose. Or I'm sorry, I don't have enough of the chlorate, potassium chlorate. Right? This is, I don't have a full 8 moles. I don't have 8 times the amount of chlorate to sucrose. So potassium chlorate is my limiting reactant. If you don't understand that, that's perfectly fine. Just pick one of the products, figure out how much product each one can make, and then the one that makes the least is your limiter, and you're good there. Okay? So 7.52, that's less than 8, which means KClO3 is my limiting reactant. All right. So now we can then go ahead and compute our enthalpy change, since we now know our moles of potassium chlorate, and that's what is determining what is actually how much is made in the reaction. So that's going to determine how much heat is produced. So we're going to take our kilojoules, and it is negative kilojoules because we're told it's produced. So that means it's given off, divided by our moles. And we get 744, technically negative 744 kilojoules per mole of potassium chlorate. Yeah. Subscript. Okay. And we can also just say it's 744 kilojoules per mole produced. And now this is per mole of potassium chlorate. And when we look at the balanced reaction, there's 8 moles in our balanced reaction. So we have 744 kilojoules for every 1 mole of KClO3. And we have in total from our balanced reaction 8 moles of it. This now comes out to be 5,960, negative 5,960 kilojoules. Okay, because it's produced, so it's a negative kilojoules. So then now, whoops. The thermochemical equation to write it out now is C12 H22O11 plus 8 KClO3 becomes 12 CO2 plus 11 waters plus 8 KCl, and then next to it we write delta H equals negative 5,960 kilojoules. Now, we often have enthalpy changes that have been already tabulated where the reactants and products are at the same conditions. And we have what's called standard state, and this is just a commonly accepted set of conditions that is used as a reference point for determination of properties under different conditions. So the IUPAC standard state is pressure of 1 bar, which is the same as 1 ATM, or well, roughly 1 ATM. 1 bar is 0.987 ATM, and all solutions are at 1 molar concentration. There's a superscript of O that is used to designate standard state conditions. A lot of times, generally, it's at 298.15 Kelvin, aka 0 degrees Celsius. So if you see delta HO, this means an enthalpy change under these standard state conditions. A lot of these changes are available in reference literature. Now you need to keep in the back of your mind, though, that delta H is extensive. It's proportional to the amount of your substances. Okay, but oftentimes it's normalized to a per mole basis as well. So things to keep in mind. You'll see why. Now we also have the standard enthalpy of combustion. So you've got the O for your standard and then the subscript of C. And this is the enthalpy change when exactly 1 mole of a substance burns. So it's being reacted with oxygen gas, aka O2, under standard state combustion or conditions. And we often call this the heat of combustion. For example, the enthalpy of combustion of ethanol is negative 1,366.8 kilojoules per mole. So if 1 mole of ethanol undergoes complete combustion at 25 degrees Celsius and 1 atm pressure, giving products that are at the same temperature and pressure, it is negative 1,366.8 kilojoules that is released. And there's the reaction for it. So here's some standard molar enthalpies of combustion. This is a good page to mark also. From methane on down, these guys are called hydrocarbons. For those of you that go on to organic chemistry, you will know all about hydrocarbons. But hydrocarbons literally means hydrogen and carbon. Technically, ethanol, methanol, and isooctane aren't necessarily hydrocarbons. They're alcohols, but still. You can see the combustion reactions and their enthalpies of combustion at 25 degrees Celsius, given as kilojoules per mole. So these are some reference reactions for you. Combustion of gasoline is very exothermic. So let's look at an example. As that picture we just looked at suggests, it's very exothermic, and let's figure out the approximate amount of heat produced by burning 1 liter of gasoline, assuming the enthalpy of combustion is the same as that of isooctane, which is a common component of gasoline, and there is its density, 0.692 grams per milliliter. So we know we have 1 liter of isooctane. So the first thing we can do is make that into milliliters so we can then compare it to density. And I'm just going to rewrite it in the notation that I do it for you guys. We have 1 liter of C8H18. And we know there is 1,000 milliliters in 1 liter. And then we can go from milliliters to grams using density. And there's 0.692 grams of it for 1 milliliter. And now we can go ahead and go from grams to mass using molar mass. And we have 1 mole of it per 114 grams. And table 5.2 tells us, oops, I'm sorry, we're not going from grams to, we're going from moles from grams. We already got grams from density. Sorry for the misspeak there. If we look at table 5.2, it tells us that isooctane gives us negative 5,460 kilojoules for every 1 mole of it. So we go now from grams to moles using density. And then we can use that the enthalpy of combustion as a conversion factor. And we know there's negative 5,460 kilojoules for every 1 mole. So our moles there cancel also. And then that leaves us with negative 3.31 times 10 to the 4th kilojoules or 3.31 times 10 to the 4th kilojoules produced. Fun fact, this is enough to melt 99.2 kilograms, or about 218 pounds of ice. Also, if you're interested in each of these numbers step by step, your book goes through that on page 261. Just an example of some biofuels. A few people I went to grad school with did a bunch of research on biofuels. A lot more work needs to be done as an alternative to energy production. But algae could potentially be a way of the future for producing fuels. So we have another type of standard enthalpy, and that is standard enthalpy of formation. And this is an enthalpy change for a reaction where 1 mole of a pure substance is formed from its constituent free elements in their most stable states under standard state conditions. So for example, enthalpy of formation of carbon dioxide is negative 393.5 kilojoules per mole, and it's carbon and oxygen combining to form CO2. And then the standard enthalpy of formation of an element in its most stable form is equal to 0 under standard conditions. This is just by definition. So for instance, if we want to write the heat of formation reactions for those two compounds in A and B, we need to first remember that the heat of formation are for forming 1 mole from its constituent elements under standard conditions. So for A, we have carbon, hydrogen, and oxygen. So we need to have 2 carbons, and graphite is the standard state of carbon. And then there's hydrogen gas. We need a total of 6 hydrogens, and hydrogen in its natural state is H2. So that would mean we need 3 H2s to give us a total of 6. And then we can say, and oxygen is O2 in its natural state. So if we say half O2, that gives us 1 oxygen. And that gives us C2H5OH, okay, or C2H6O. For calcium phosphate, this is made up of calcium. We need 3 of them from the formula. And phosphorus has a standard state as P4. This isn't something I expect you to know. This is just kind of something they're telling you. And if it was on an exam, I would also say, like, hint the standard state of phosphorus is P4. And I need 2 phosphorus since there's 2 PO4s. So that means I need half of a P4 to have 2. And then I need a total of 8 oxygens, so I need 4 O2s to give me calcium phosphate. So this is what it means by writing the heat of formation reaction equations. Okay. Now, Hess's law is where we're going to spend a good amount of time talking, because it's kind of complicated. So there's 2 ways that we can figure out the amount of heat in a chemical change. We can either measure it experimentally, or we can actually calculate it from experimentally determined enthalpy changes. And there's some reactions where it's pretty much impossible to try to do this experimentally. So we use Hess's law. And Hess's law uses the fact that enthalpy is a state function. Okay, and so what it tells us is we can take a process, a chemical reaction, and break it down into a bunch of stepwise reactions, and then that totals our final reaction. And the sum of all those delta H's is the enthalpy of our reaction. So again, enthalpy is a state function. It depends only on where a process starts and ends. We don't care about the path it takes to get there. So this is why Hess's law is valid. So for example, let's say we want to look at the reaction of carbon and oxygen to form carbon dioxide. The direct process is C plus O2 becomes CO2. Delta H is negative 394 kilojoules. But if we want to do this as a two-step process, we could see that carbon and half an oxygen gives us CO, and then that CO and half an oxygen react to form CO2. And if we sum this up, okay, what we find is we have CO on both sides. This is kind of like what we did before with the half reactions. Okay, and then half an oxygen and half an oxygen form one oxygen. And we get the same net change as the overall reaction. And we also get the same delta H, negative 394 kilojoules, which is the same as the overall reaction. So it doesn't matter if our reaction happens in one step or two. So this is kind of just an example of what's happening, going from carbon and oxygen combining to form CO2. Whether it goes in one big step or two smaller steps, we're still getting to the same place and we still have the same delta H. Okay, so this is still all overall the same delta H change in enthalpy. So we can use Hess's law to figure out the enthalpy change of any reaction as long as we have enthalpies of formation for the reactants and products. So there's some of the reactions we might use are decompositions of the reactants into their components or recombinations of elements to give products. So the standard enthalpy change of the overall reaction is equal to the sum of the standard enthalpies of the formation of all the products plus the sum of the negatives of the standard enthalpies of the reactants, aka the sum of the products minus the sum of the reactants. Okay, so that big sigma, Jeff, what's that symbol? I'm forgetting it right now. Is that sigma?
Yeah.
Okay. Thank you, Jeff. The big sigma is the sum of the n, and so the n represents our coefficients, stoichiometric times our delta H for the products minus that of the reactants. So let's look at an example. We want the standard enthalpy change for this reaction. And so what we can do is we look up the delta HF of our various parts. Where am I in my book? Oh, there it is. Okay, and I'm going to bring up another example after this one. So we're doing this example, then I'm going to go back to a different example. So if you go to Appendix G, there's some enthalpy of formation values. And what you would find is that for the products, HNO3, nitric acid, our first one, it has an enthalpy value of negative 207.4 kilojoules per mole. And in the stoichiometry, it has a 2. So that means we need to multiply it times 2 moles. And then our other product is NO, and we find its delta H back there, and we have 1 mole, so it needs to multiply it times 1, minus our reactants, NO2 and water. And when we add that all up, we get negative 138.4 kilojoules. Okay, I am going to go to a blank screen because the PowerPoint provided by the book people gives a very important example of using Hess's law and doing stepwise calculations. And I'm going to do the more challenging one. This is example 5.14 in your book. And I will probably have to delete the slide and continue to go because it's going to take up a lot of room. So we're told that chlorine monofluoride reacts with fluorine to form chlorine trifluoride. Okay, and we're given this, they give us the reaction, they tell us everything is a gas. And we want to know what delta H is. So what we can do is we go to Appendix G in our book and we look up we look up reactions that could add up to make this overall reaction. So Appendix G is a lot, actually it's not Appendix G we want, we're actually given the equations. There are appendices that also will give you the smaller equations that you need. I've always kind of called the mini equations. Appendix G just gives you standard thermodynamic properties themselves. It doesn't give you actual reactions, which is also kind of nice. But we're told to use the following reactions. So it calls this 1, and then reaction 2, 2OF2 gas comes O2 gas plus 2F2 gas, and we're told this one's delta H equals negative 49.4 kilojoules. Next reaction, 2ClF gas plus O2 gas is Cl2O gas plus OF2 gas. And this one's delta H is positive 205.6 kilojoules. And our last equation, ClF3 gas plus O2 gas becomes 1/2 Cl2O gas plus 3/2 OF2 gas. And this one's delta H is equal to positive 266.7 kilojoules. Okay, so what you should see here is that there's some things here that aren't in our overall final equation. So we know those need to cancel out. So we need to change some things around in our equations, in our little mini equations, as I call them, so that we get our reactants on the right side and we have the correct numbers and all that fun stuff. So one of the first things is we need to manipulate equations 2, 3, and 4 to get them to add up to equation 1. So let's look at equation 1 though, and we see ClF and F2 are our reactants. So let's look for equations that have ClF and F2 in them. And I see, okay, equation 3 has ClF, and equation 1 has F2. So those look like ones that we're going to need to have on the left side. So starting with equation 2, let's flip it around because I need that F2 on the reactant side. So I'm going to go ahead and change my ink color. So by taking this and going, okay, now this is O2 plus 2F2, becoming 2OF2. Since I did that, that means I have to change my symbol of delta H for equation 2. That is now equal to positive 49.4 kilojoules. Since we reversed the sides, we have to reverse the sign. And then I also notice for equation 2, for the ClF, I see that equation 3, has a 2 in front of it. But my equation 1 shows me, my original equation, I only have one of them. So I need to take equation 2, I reverse these two, and I need to take equation 2, well, no, and I need to divide it by 2. of a... Okay. 2OF. So annoying. OF. Stop it. Use a white screen. How about that? So that way I can see better where I am. Okay. So equation 2, I have 2OF 2O2 plus 2F2. Again, this is example 5.14 for those of you following along. Third 2CLF plus O2 OF2 and equation 4 Okay, so one other thing I didn't really touch on was what I would do is I go back and I look at the little mini equations and I look at what they have in them that I have in my overall reaction that I care about. So what I need to end with, for instance, I know I need this fluorine, and I know I need fluorine monofluoride, and I need chlorine trifluoride. That way I can just kind of see where they are so I can remind myself this is what I need to get to. I'm going to go back to my pen. And let's go back and look at our reaction. So reaction 2, and actually really quick, I'm going to write my overall reaction kind of on the bottom so I remember what I'm looking for also. Okay, so in reaction 2, mini reaction 2, on the top, I've got my fluorine that I need, but it's on the product side, and I need it on the reactant side. So I need to flip this reaction, and it has a 2 fluorine, when in reality, I only need 1. So on top of that, I need to divide all of this by 1/2, or multiply it by 1/2 divided by 2. So now this reaction can be rewritten as 1/2 O2 plus F2 becomes OF2. At the moment, I'm just going to kind of ignore their states of matter. I know they're gaseous already. Delta H now is, it's negative 1/2 since we're flipping it. That means flipping the signs. So now delta H is positive here. And 49.4 divided by 2. So it's positive 24.7 kilojoules. Now equation 3 has the chlorine monofluoride that I need, but it has 2 of them. So this guy, I need to divide by 2. I multiply times 1/2, so that way I get it correct. That's the only change I am making. So now this can be written as CLF plus 1/2 O2 becomes 1/2 Cl2O plus 1/2 OF2. And our delta H is also getting halved. So now that's positive 102.8 kilojoules. And in equation 4, that has our chlorine trifluoride that we need as a product. So that means we need to do the old switcheroo, which means we also need to reverse the sign on our delta H. So now rewriting that, we have 1/2 Cl2O plus 3/2 OF2 becomes ClF3 plus O2. And this delta H now is negative 266.7 kilojoules. So now we're going to add up this system. Get a different color. Let's go green. And let's look for things to cancel out. So one thing I noticed, I have half an O2 and half an O2. Those add up to be 2/2 O2, which equals 1 O2. And look at that, I have 1 O2 here. Boom, boom. Those guys cancel out. Now I have 1 OF2 and a half OF2. Those two add up to be 3/2 OF2. And then I have that on the right, have it on the left. They cancel out. 1/2 Cl2O on both sides, they cancel out. So then if we rewrite everything, we now have F2 plus ClF and ClF3. So our overall reaction checks out, it's the same thing. And our delta H, we're going to add these three values up and get a total of negative 139.2 kilojoules. So that is another way you can use Hess's law. You use the little, like I call them baby reactions, to get your overall delta H. And then the example we did before this uses appendix G to get values of delta H that are for just each individual compound. So that does it for chapter 5. I know this was kind of a very involved chapter, especially being only 3 sections. Take your time with this, especially since you guys are taking your exam right now as well. Don't overload yourselves. Next week is an easy week too. We're starting chapter 6, so there's not really gonna be any homework, just a discussion board for next week. So take your time with this stuff as well. All right, again, let me know if you have questions on any of this, on the homework, etc. Otherwise, I will see you all soon.